So we're ready for Lecture 2 in Chapter 8, and we're going to begin to build a model that can handle technological progress. Let me give you kind of a preview of the result. The result is going to turn out to be really simple. Now we're going to take kind of a long, drawn-out way of getting there, but the ultimate result is, well, we're just going to change our break-even function. All right, we're going to add one more term to our break-even function. That'll be the ultimate result, but we do need to be able to justify why we add one more term to the break-even function. So I'm going to take a little bit of a kind of a meandering tour to get there, but I'll try to be as concise as possible. So, technological progress, we need a new variable. A new variable is going to be E, labor efficiency. So rather than change the production function, right, which is, well, really what technological progress means is that the production function changes. If we're able to an economist, an increase in technology simply means that we're able to take the same capital and labor, same amount of inputs, and get more output. So no change in resources, we just are better at using them, and so we can get more out of it. Okay? Easy peasy. I mean, it's just, for example, if you give me a typewriter and ask me to type out a book, it's going to take me a long, long time, and it's going to have lots of spelling errors because I'm bad at spelling. Well, if you give me a computer with my cool spell check on it, well, then it's going to be a lot faster. I'm gonna have much more productive. So that was an increase in technology. All right, you give me the computer with a word processor on it instead of the typewriter, then you get more output in a shorter amount of labor input. So we can increase my labor efficiency, which is exactly what we're going to say. We're going to say that new technology makes labor more efficient. And instead of trying to change the production function, what we're going to do is we're just going to say, well, let's say you're twice as efficient as you were. Well, let's just count you as 2. Right? So we're going to essentially hold labor, right, the L parts, efficiency constant, and split that out and take care of that by adding in this variable E. Okay? So, assume technological progress is a labor augmenting. What does that mean? And what we're doing is this is the labor augmenting method or labor augmenting approach to technological progress. And what does that mean? That means that, well, just what I said. An increase in technology means an increase in the efficiency of labor, and we're going to make another big assumption. That increase is exogenous. All right? We're not allowing the model or inside the model or any kind of endogenous. That's endogenous growth, and it's really cool stuff and much more modern and where we need to go with this. But for now, we're just going to take it as given. We have technological progress. Okay? And that technological progress or technology improves at rate G. So G is just the growth rate of E. What is E? E is this variable that's augmenting labor efficiency. And to be honest, E, it turns out not to matter that much. It's that G, that growth rate in technology, that's important. Now, we're going to rewrite the production function as Y equals a function of capital and L times E. And we're going to redefine that as a new variable. We're going to call that effective labor. So what is effective labor? Effective labor says, well, wait a minute. If you're twice as productive as you were in 1950, well, we're just going to multiply you by 2. So we'll treat you as 2 people. That way, we can kind of keep it constant. So we'll keep L in terms of how productive you were in 1950, and we'll use E to adjust for the fact that, hey, you're a lot more productive today. Okay, so we call this effective labor. Okay, and another way of saying that is the number of effective workers. Now remember, we're going to use this word effective a lot, so you're going to get sick of it by the end of this chapter. Increases in labor efficiency have the same effect on output as an increase in the labor force. That's what we're saying. That technological improvement simply improves the productivity of labor, and by improving the productivity of labor, what are we doing? We're essentially just increasing the labor force. That's how we're going to model technological advancement. Now you're saying, well, is that kind of a cheesy way to do it? Well, maybe it is. It's definitely a trick. All right? We don't really believe that's exactly how it happens. Because, well, wait a minute. Couldn't technology also improve the productivity of capital? Sure it could. And there's actually other models. We can even have other models like this that could achieve the same goal somewhat similarly. You might like them better. It doesn't matter. We're going to end up with the same result anyways, and the math here is better. So what we're going to do is we're going to stick with this model because mostly the idea behind this is to teach you how to use these models and to begin to think with these models. So we're going to crawl before we run and keep moving forward. So we need some new notation. Little y is no longer output per worker, it's now output per effective worker. Little k is no longer capital per worker, it's capital per effective worker. Okay, we're going to put that effective in there. Why? Because we're adjusting for technological progress. So our production function becomes y is a function of little k, where y is output per effective worker, and this is the per effective worker production function. All right, so big difference there is what? We're adjusting for technological progress, or at least we're allowing for it. Now the savings function becomes, well, guess what? Notationally, it looks exactly the same as it did in Chapter 7, right? Except we know underlying these there's a little y is big Y divided by L times E, and, well, little k is, well, big K divided by L times E, right? So we had that times E in there. But notationally, by the time we get it all said and done, it looks the same. So don't let this be too confusing. Now, the break-even function. Here's the deal. What happens if technological progress increases in this model? It's the same thing as if we have more workers. In fact, that's exactly how we're modeling technological progress, that it mimics just having more workers. And so we're going to take into account the growth rate in technology in the exact same way we take into account the growth rate in population. And therefore, as we have an increase in technology, we're going to need more capital per worker. And so we have to add in to this break-even investment plus G. Now, I want to take a step back and think about this assumption for a minute. Because frankly, guess what? This is probably a cheesy model. You're probably rolling your eyes right now as you're watching this video thinking, come on, can't we model technology in a way that's a little more realistic? Well, we could, but let's think about this for a second. As technology is improved, do we need more stuff? I mean, let's think about it. And I'm gonna be selfish here and talk about being a professor, because that's what I am and what I know how to do, and so I'll kind of rest on what you know there and think about, well, what did you need to be a professor, say, in the 1950s? Well, let's face it, you needed some books, desk, maybe a lamp to be able to see at night and to read by. Reading glasses were good, pen and paper, and probably a typewriter. Okay? Yeah, you didn't need a calculator because guess what? They didn't have calculators. And you didn't really need a computer because guess what? Well, they didn't really have computers, at least not the way we have today. You didn't need all that stuff, right? Why? Because you didn't have it. All right, well, let's fast forward a little bit to the future, like say 2013. What do you need? Well, you need a laptop, you need an iPad, you need, let's see, just to teach this class, I've got a laptop, I've got an iPad, I've got software that does video capture of my lecture, I have a wireless internet connection and Wi-Fi connections. Oh, I've got all kinds of stuff going on here just to teach this lecture, right? Look at all the capital that's coming in teaching this. Right? Well, what's happened? We've had technological progress. So, along with technological progress comes the need for more capital per worker. So, while we might say this is kind of a cheesy model, the actual prediction or the implication of this assumption definitely seems to meet with reality. So, just because an assumption might sound a little bit cheesy or not very realistic doesn't mean it's a bad assumption. If the predictions that come from that assumption or the implications of that assumption match up with reality, and they help us study the particular part of the system that we're interested in, the phenomena that we're actually interested in, then it's okay to have a cheesy assumption. Okay, so we see that the break-even investment is simply the amount of investment needed to keep K constant, and it's just what? We have to account for the amount of capital we destroy, the increase in the workforce, and the increased productivity of the workforce, and multiply that all by K, and that is our break-even investment function. And notice, what's the difference? We added in a plus G. I told you, we've got to take a long route around to be able to justify adding that plus G in, but by the time it's all said and done, yep, that's all we're going to end up doing to our model. Yep, okay, yep, we talked about all this stuff, right? You got that? All right, if you need to pause and read over that, pause the video right here and read over that. Okay, so now we have to figure out, what's the steady state? What's the law of motion? What's all that good stuff? Well, law of motion, guess what? Is exactly what it was before. It's delta K. All right? Because every variable inside us, all the endogenous variables in this model are functions of capital per effective worker. And so, delta K gives us the law of motion. And the law of motion is just simply the investment function minus the break-even function. And guess what? The only difference is we've added in that minus G. Now I want you to notice something. What happens if the growth rate in technology is 0? Then the minus G goes away, right? And what do we have? Delta plus N times K, which is exactly what the model was when we simply had population growth. What happens if the technological growth is 0 and the population growth is 0? Then N is 0 and G is 0, and all we end up with is delta times K, which is depreciation. It's exactly the model we started out with at the beginning of Chapter 7. So notice what we've done is we've just simply made our model a little more general, a little more general, and a little more general by relaxing some assumptions. At the beginning, we assumed no technological growth and no population growth, and we've just relaxed those assumptions. That's how we build a model oftentimes. So, what's steady state? It's steady state is where delta K equals 0, right? So, delta K equals 0 when the break-even function equals investment. And so we have our steady state level of capital. And if we came right over here, we get steady state level investment per worker. If we add in the production function, right, we get steady state level of output per worker. The difference is consumption per worker. Everything stays the same. The only difference is we've added in the plus N and the plus G from the beginning of Chapter 7. Now, the next thing I want to look at is I want to take a look at the growth rates of all of these variables in the steady state. Because remember, we motivated Chapter 8 by saying, wait a minute, you're telling me output per worker should be constant, but guess what? It doesn't stay constant. So the model that we had by the end of Chapter 7 just doesn't work when you take it to the data. Will this one? Well, first of all, capital per effective worker. Well, in the steady state, what happens to capital per effective worker? It's 0, right? Right? Remember, per effective worker, it's going to be 0. It's in the steady state. Output per effective worker. What's it going to be? 0. It's in the steady state. All right, next, output per worker. Now, there's a difference here, right? The difference is it's not per effective worker. It's per actual worker. So, it's not little y. Little y is not output divided by labor force. It's output divided by labor force times the effectiveness factor, right? This productivity of labor factor. So if we want to get output per worker, what do we have to do? We've got to multiply little y times E. Now, what is the growth rate of that? Well, I'm telling you it's G, but let's take a step back for a second and let's take a look at that. So, I know that output per worker, in this case I'm going to write it big Y over L, because why? Well, I don't have little y anymore to be output per worker, because little y is output per effective worker, which equals little y, all right? But little y is what? Little y is, right, little y is big Y over L times E. I want to be big Y over L. I have big Y over L times E. What do? Well, multiply both sides by E. So if I multiply this side by E, what happens? The E's cancel. If I multiply this side by E, what do I have? I have Y times E. So big Y over L, or output per worker, has to equal little y times E. Now, here's the thing. How do I figure the growth rate of a variable? Well, the rule is the growth rate of a product, or something times something, is equal to the sum of the growth rates. So I can just take the growth rate of little y and the growth rate of E, add those two together, and I get the growth rate of y times E. So what's the growth rate of little y? Well, in steady state, the growth rate of little y is what? 0, right? Remember, steady state output per effective worker always grows at 0. All right, what's the growth rate of E? Well, we've already defined that. That's G. So 0 plus G equals the growth rate of output per worker has to equal G. Next, the growth rate of total output. Well, the growth rate of total output is, if I want total output, I want Y, which equals what? Little y, which is big Y divided by L times E, and I better multiply by E to get back output per worker, but then I better multiply by L to get output, and now I know that this guy grows at rate 0, this guy grows at rate G, this guy grows at rate N, and so I know the growth rate of output is what? N plus G. All right, that's the growth rate of output. So if I come back here, I see, wait a minute, what are the growth rates that are implied by or predicted by the solo growth model with technological development? Well, capital per effective worker, 0. Output per effective worker, 0. Why? Because we're in the steady state. But what's output per worker? It's going to grow at rate G. What does our data say? Our data says output per worker grows. What does this model say? Output per worker grows at the rate of technological improvement. So we now are consistent with the data as far as output per worker growing. Also, we have another kind of stylized fact that comes out of the data, in that the total output grows faster than the population. Well, that's the only way that output per worker is going to grow, is if total output grows faster than the population. And what do we have here? We have the prediction that total output is going to grow by the population growth rate plus the technological growth rate. And so that's going to be greater than, or at least greater than or equal to, the population growth rate. And so our model now fits much, much better with the data that we see than we did before. So what's the golden rule with technological progress look like? Well, what I ought to do is give this as a homework assignment and see if you guys can figure it out. I'll bet you can. We want to do exactly the same thing as we did before. We need to express C star in terms of K star, and so we start same national income accounting identity we had before, substitute the production function in for Y star. We're going to substitute in the break-even function for investment star. And why do we do that? Because in equilibrium, the investment function must equal break-even investment, because that's the steady state. Okay, and we end up with that. And notice all we did was added in the plus G. If we take the derivative of that and set it equal to 0, we end up with the marginal product of capital equals delta plus N plus G, which we can rearrange to equal MBK minus depreciation. So you can kind of think of this as kind of the productive parts of capital, or the parts that are intrinsic to capital, right? How fast capital wears out, that's due to capital. The productivity of capital, that's due to capital. And then you have over here kind of these exogenous things, technological improvement, population growth, that are a little less to do with capital. So, I mean, that might be one reason to break them up. I really don't care if we split them up or not. It says, or equivalently, right? They are definitely equivalent because we're just solving algebraically. All right, that's the golden rule. So in the golden rule steady state, the marginal product of capital net depreciation equals the population growth rate plus the rate of technological progress, right? Exactly. All right, we will continue with the next lecture, but just remember, all we've done is just add one little more part to the puzzle. So don't make it any more difficult than it has to be. We just added one more piece.